Alright, hello everyone. I'm gonna do a little intro to the lesson that we're having tomorrow, and also a bit of recap of what we talked about in the last lesson, because we went over quite a few things and it's important that it's fresh in your mind when we get to the class tomorrow. Alright, so what did we do in the last lesson? I got you to think a little bit about the significance of electricity as an invention, what life would be like if you'd never had it, and things like that. And I forgot, we all forgot to talk about something that we all really like and we wouldn't really have that much of. We wouldn't have a lot of music if we didn't have electricity, and all those really fancy headphones, monster beats and all of that stuff you wouldn't have to play with. So you'd have to go and find much more live music, people who knew how to play, and you'd be going to more concerts and stuff. And people wouldn't do that as often as they play music right now, just off their stereo. So there just would be less music in your life also, which I think is significant. Anyway, after that brief homage to music, I then got you to think about whether you knew enough, after having been using these guys for a long time in your life, about batteries, to be able to perhaps go about inventing one if you went back in time and the whole of civilization depended on you, whether you could construct a battery of your own. And we concluded that we needed some chemicals, and some reactions had to happen inside of the chemicals, and that these reactions would have to separate charge, perhaps using an acid and an alkali, but the idea was to use an electrolyte, which is a type of liquid which has ions, and the ions are charged atoms, and to separate these ions and create an electric potential by separating the negative ones on one side and the positive ones on the other. And we also said that copper was a conductor, so you could use copper, thin filaments of tungsten if you wanted a light bulb, for example. The filaments of tungsten, you could make the current go through there after it being going through the copper. And so by going through this really thin wire, it would heat up because of the resistance, and this would give off light, and you just invented electricity. So the key there would be to find the right liquid with the ions and mix them together to get the reactions that you want, to be able to create some electric potential, which was the magic word there. Why did we need electric potential? Well, we have a bunch of electrons sitting on a wire, a lot of them inside of a wire, and we want them to move. We get them to move, we need a positive thing here to attract them and a negative potential here to repel them, and then we'll get them to move. These need to be in a complete circuit, because otherwise they start bunching up, and they queue up, all of them in one place, and very few here, and they wouldn't like to do that because they want to be separated from each other, so they just would not flow if you just have them open-ended and you don't give them a complete loop for them all to be able to move at the same time, one in front of the other. We talked about that idea. And we also talked about the fact that the energy transferred to the electrons themselves, the charge carriers, was called the EMF, the electromotive force. And the electromotive force is called like that because of historical reasons, but it's not really a force. It is well, what is it? It's measured in volts, and it is an amount of energy. Okay, it's the amount of energy that you give to each unit charge. So it's measured in in joules per coulomb. Thank you, Raul. And so this is energy given to the electrons by the battery. Okay, so that's we call that EMF. So EMF is measured in volts, and this energy given to the electrons by the battery, and you measure it in energy per unit charge. So that's joules per coulomb. Okay. And we also had this other idea which was similar to the EMF, which was called potential difference, right? And it was also measured in volts, but it had to do with the amount of energy given by the electrons to the components in the circuit, and it was also measured in volts, which is joules per coulomb, and to ask a circuit what the potential difference is between one point and another. So here's a circuit, we'll be drawing some other ones tomorrow. To ask a circuit, hey, what's the potential difference between here and there? You always have to talk about difference between 2 points, right? We'll talk about more about that tomorrow. But if to ask that, what is the potential difference, would be the same as putting a voltmeter here in the way and measuring the volts between this point and that point. And that question would be analogous, would be exactly the same question as saying between this point and that point, how much energy did you give away, in this case to the light bulb? How much energy did you give away to the light bulb? And the answer would be, well, if each coulomb of charge gives 3 joules of energy, then the potential difference between those 2 points is 3 volts. Right, so hopefully that makes sense. And the if instead of that each coulomb gave 10 joules of energy away, then the potential difference between the 2 points would be 10 volts, right? So if the energy per coulomb between here and there has been 6 joules, then we can say that a voltmeter here would read 6 volts, okay? And if that reads 6 volts, that means that the potential, that the EMF supplied by this battery has to be also 6 volts, because the electrons can only give away the energy that they collect at the battery. Okay, so if the EMF is 6 volts, then this will be 6 volts. If you start putting more bulbs, then the voltage starts splitting up, but the total sum of all the volts, of all the potential differences across the circuit needs to be equal to the EMF. We'll talk about that more tomorrow, but hopefully this gives you an idea already about things we were talking about the other day. Okay, now the charge of an electron is quite small. Okay, so 1 coulomb sounds like a small charge, but it's actually a lot of electrons. The electrons have such a small charge in them that only in 1 coulomb you have these many electrons. It's like a 1 with 18 zeros after it, so this is a gazillion electrons. So really, when you say 3 joules, 3 volts, then 3 volts is being carried by that many electrons. Okay, so 1 joule is really a huge amount of energy for an electron. These are tiny. Alright, so having said that, you know, remember that when we say volts, we mean 1 volt is the same as 1 joule per coulomb. Okay, and in 1 coulomb you have lots and lots of electrons. You don't need to know that number, it's just an impression to give you. Okay, 1 coulomb is a lot of electrons. Okay, hopefully that makes sense. Now let's go to the next part. So then we also talked about current. Okay, and we talked about current as the flow of charge from one place to the other, right? The rate of flow of charge. So current, the equation that we had was I is equal to, let me use a different color here because otherwise I'm not highlighting anything. The current is equal to the charge divided by the time, in the sense that we had this triangle, and we said, well, if Q is at the top, Q is going to be at the top here. And we also discussed in one of the classes anyway that it doesn't matter if it's I and T or T and I at the bottom, right? Because it doesn't matter if you do IT or TI when you multiply them. It really doesn't matter. 3 times 4 is 12, and 4 times 3 is, guess what? Also 12. So it doesn't matter if the triangle is that or the triangle is this one. But the Q has to be on top, because it does matter when you divide what's on top. Right? Now, let's see. What is the meaning then of current? Well, if it's flow of charge or rate of flow of charge, it's the same as saying the charge passing one point in the circuit divided by the time they take, by the time that charge takes to pass that point. Right? So if I am here in a wire and I have some kind of net or some way of counting the charge that goes through, then if 40 coulombs of charge goes through in a second, then that is my current in amps. Okay, so I, which is the symbol for current, would be 40 amps. Okay, so I've got a couple of examples here, so let's see. It says if 20 coulombs of charge pass one point in the circuit every 1 second, then the current is 20 divided by 1 second, so that's 20 amps of current, right? If the 20 coulombs, instead of taking 1 second, took 2 seconds of time to pass, then you divide the current, the charge of 20 coulombs by the 2 seconds, and you have a current of 10 amps. 10 amps is half of this much. Why? Because it takes twice the amount of time to go through, and here we're talking about the rate of flow. So if it takes if it takes 2 seconds instead of 1 second to go through a point in the circuit, then the rate is half as much. It's half as much because it takes twice as long. So you divide by 2. If you divide by 4, then you're going to have an even smaller current. So the longer it takes the time for the charge to pass a point, the smaller the current. Right? This also depends on the amount of charge. If I have 40 coulombs going through the circuit, through a point in the circuit every second, then my current is 40 amps. If 40 coulombs take 2 seconds to flow, then my current is 20 amps, and so on and so forth. So that those are all examples of using this equation. Current is equal to charge divided by time. Similarly, you can use the equation to ask a different thing. Well, if current is equal to charge divided by time, then surely from my triangle, then I can use the same equation to find out what the total charge is. Charge must be current times time, right? Because I cover this guy, so then current times time must be the charge. So if current multiplied by time is charge, then I can ask, okay, if I have a current in a circuit of 20 amps and 2 seconds go by, then how much charge has flown through the circuit in those 2 seconds? Well, then charge is the rate, which is the current, times the number of seconds, which is 20 amps, times the number of seconds, which is 2. So the answer would be 40, and the unit of charge is coulombs. Coulombs. You don't have to write it like that, you can just write 40 C, but always write the units, right? Don't forget it. Physics is really important to write the units. Okay, what else? So something that I would like you to think about for tomorrow, right, is that you can think in GCSE, you can always think of electric charge as water when it's flowing, okay? And static charge is different because you've got positive and negative charge, and they're not flowing, they're repelling each other and stuff like that, so you don't have positive and negative water. So it's not so useful for static electricity like in the last topic, but it's very useful for this topic. So electric charge, when it's moving, you can think of it as water in GCSE, and so the electric current is similar to water current, and it is similar to the rate of flow of water per second, right? So if 20 liters of water place in a pipe per second, then the current would be the same, would be 20 liters per second. So the electric charge would be 20 coulombs per second. So a coulomb and a liter are analogous to the degree that we're learning here, and you can think of quite well of the charge moving around as water. Now, just as to make that analogy a little bit more intuitive, I forgot, I just mentioned about current, but I forgot to mention voltage. Voltage then, or the potential difference, you can think of as the difference in energy being carried by the water, okay, or the energy given to the water. So the voltage or the potential difference, you can think about it as the energy that the water uses as it moves around, it loses energy, or by the energy given to the water. So let's look at this analogy at this little model here to understand it a little bit better. This will help a lot in the class of tomorrow. So here I've got a bunch of water at the bottom of this little container, and here I have a pump. And pumps do some really clever things. There's lots of different types of pumps, and someday I can tell you a little bit about them. So I used to work in a place where we had lots of pumps. But let's pump this water all the way up here, and what happens? Well, let's think about first what the analogy of this pump is. Well, if I had a circuit, the equivalent of the pump would be the battery, and the long side of the battery is always the positive, and we always say that current goes from positive to negative. Let's say this is a light bulb and it's connected to the battery. Okay. So current always goes from positive to negative, even though electrons actually go the other way, and we'll talk about that at some other point. Don't worry too much about that, but that's just convention and a bit of historical bad luck. So current goes in that direction, and the pump here is represented by the battery. They're the same thing. Here's all the charge, and the water goes up, and the pump is doing some work. It's actually giving some energy to the water. How is it doing it? Well, it's increasing its height, and in physics, if you have height, you have energy. It's called gravitational potential energy. We'll do more of that soon, but this amount of energy that you're giving to the water to increase it is the equivalent of the EMF, which we were talking about, the amount of energy given to each coulomb of charge, or the amount of, in this case, gravitational potential energy given to each liter of water. Now the water falls down into here. Let's not change the color of the water. When it gets here, it can now do some work. All the energy that the pump has given it can do some work. So it falls into here, then it falls into here, and I can, as it's falling into here, I can put it through a little windmill, and it can do some work on the windmill, and that windmill can then do some useful things for me. And that's corresponding to the battery here. So as it goes through the battery, it loses some energy and it gives it some. Okay, imagine that there was other bulbs here and other things, then it would do other drops, and eventually it would get to the other side of the wire, which is this side, and by the time it gets to that side, then the current, we say, has done all of its work. It's given all of its energy to the circuit, and so this has zero energy down here, and it goes back into the pump to be put through again. Okay, so hopefully that model makes a little bit of sense to you. The current I would therefore be how much charge is flowing per second through any one point. So how much water is flowing per second, and the voltage is potential differences. All the little drops here are potential differences, because they are bits of energy that the charge is giving as it moves, and this is the EMF, which is the charge given to the water. Okay, so we'll talk a little bit more about all of this tomorrow, but I thought that this introduction was very important to save a little bit of time tomorrow and to give you a bit of sense of what we'll talk about. Okay, and just to finish quickly, what we'll do tomorrow is that we'll do a few group exercises together, talking about the conceptual maps and the things that I've given you, and there I'll show you another learning trick which I think is really useful and you can use for all your studies. And then we will think about two main types of electric connections when you do circuits, and they are in series and in parallel, and they're very useful to know about and quite interesting, I think. So sorry that this took a little bit longer than the last one, but there was a little bit more to talk about, and hopefully tomorrow's lesson will be fun. Please make sure you do your homework with all the symbols that you had to define or describe, and the conceptual maps, and I'm sure I'm forgetting a third part. Well, there's two of these, and the symbols was the homework really. Alright, so I'll see you tomorrow then. Bye bye.